actual definition of an integral, we saw that it's the exact area under a curve, or that's one way to interpret it. I'll call them back. That's one way to interpret what an integral represents. And you can approximate an integral by finding a Riemann sum. That was another thing we had defined on Friday. A Riemann sum is just calculating the areas of the rectangles like we had done before. So what we were doing in 5.1 was actually evaluating a Riemann sum. We just hadn't defined what a Riemann sum was, and then a Riemann sum is an approximation for an integral. So this value we found here would be the approximate value of an integral. We could say that this answer is equivalent to, or it's approximately, I should say, the integral from our a to b, which is 0 to 3, of our function, which was x cubed minus 6x, and then dx. So this was a Riemann sum using right-hand endpoints with 6 intervals or 6 rectangles. That is an approximate value for this integral. So for now, if you're asked to approximate an integral, you can approximate that value by doing what we had been doing in 5.1. Example 3 is a little different because you're not approximating the integral, you're actually evaluating the integral by interpreting it in terms of areas. So knowing that an integral represents the area under a curve can help you evaluate some integrals. So what I'm going to do is actually, and if you have your graphing calculators, this could help, but if not, you can look up here at mine. I'm going to graph this function, y equals 2 minus 2x, on the interval from 0 to 4. Okay, this is what the graph looks like, or if you're pulling it up on your calculator. I just still had the y values from negative 10 to 10, but 2 minus 2x is just a line from 0 to 4. I'm actually just going to sketch this on my page so I don't have to have my calculator sitting there. And I can see from the graph, and I could actually verify this just by substituting values in here. So when x is 0, that y value is at 2. And then where this goes through the x-axis, it does actually go through exactly at 1. And then when x is 4, again, I could substitute 4 into 2 minus 2x, so that y value is negative 6 when x is 4.
But how do you know like the end value?
We don't need an n value for this one. So I'm going to show you, we're finding this one a different way than we did up here.
Oh, okay, that's not a curve, right?
Correct. Yep, this one's just a line. So this may not be the perfect drawing to scale, but I know that this point here is at 4, negative 6. So what happens here when directions say, or even if the directions don't say this, right now you're able to do this. If you see, as in this graph, knowing that the integral represents the area between the curve or the line and the x-axis, so we have an area here that is a right triangle. We also have, if I just draw a line here for that boundary, we have a second right triangle that lies below the x-axis. So what we can do is we can find the areas of these two triangles The one above the x-axis would be a positive area. The one below the x-axis would be a negative area. So then we would take, say I call this one a sub 1 and this one a sub 2. We would then take a sub 1 minus a sub 2 and we would get the exact value of that integral just by using areas with the graph. Okay, so if I'm just going to put here, this is a sub 1 minus a sub 2 based on how I labeled it. Area of a triangle, how do you find that? Just making sure you guys know area formulas. Thank you. All right, so the area of that top triangle would be 1/2 times the length of the base would just be 1. And the height is 2, so that's why I was labeling where everything was intersecting. And then the area of that second triangle, so it's minus the area of the second triangle, so minus 1/2 times the base has a width or length of 3 units and a height of 6. If you said the height was -6, then make sure you're adding these. So then we would have the area of the first triangle is really just 1 minus the area of the second triangle is 9. So the integral, the exact value of the integral, the net area is -8. So you will see questions where they may give you the graph of a function and ask you to evaluate the integral. Knowing that the integral is the area between the curve and the x-axis, you can use area formulas you already know, as long as you can make shapes you already know, like rectangles or triangles or circles. If not, if it's a no calculator question. Okay, are there questions on that type of problem? Okay, so I will say example 4 is a similar type of problem. I do want to move on to the midpoint rule and go through example 5. And then we'll be covering properties of integrals in a few minutes here. So midpoint rule is also something that you've really already done. So all it says is another way to approximate an integral is by finding this summation and the x sub I bar that is here just means that you are using the midpoint of each interval as the x value at which the height of the rectangle is occurring. So it's basically saying estimate the area using rectangles and using the heights as the midpoints of each interval. That's what the midpoint rule is. It's just giving it a specific name. So finding delta x is the same. It represents here x sub I bar is the midpoint of any given interval. So example 5 says to use the midpoint rule with n equals 5 to approximate this integral. So how I would start is I would find delta x so that you can figure out your intervals that you're working with. Yep, delta x, your a and your b are given in the integral from 1 to 2. So 2 minus 1 over n is 5. So 1/5, or you could write that as 0.2. And then I'm going to write out the intervals we have. We're starting at 1 and going every 0.2. We have 5 intervals. So we'd have 1 to 1.2, 1.2 to 1.4, and so on. Okay, this is really up to you if actually writing those out is helpful. It's helpful to me, that's why I write them out. And then since we're using the heights to be the midpoints of each interval, I'm just going to write down what those x values are. So the x value I'm using from interval 1 would be the midpoint of the interval. So I'm using 1.1 as the x value. And then 1.3, 1.5, 1.7, 1.9.
God bless you.
All right, so then I would say the integral from 1 to 2 of 1 over x dx. And that means our function is 1 over x. So this is approximately equal to, and I'm going to put here then m sub 5. So I'm using the midpoint rule with 5 intervals, 5 rectangles. And that's equal to, let's see, I would have for my first height would be, well, I'll write it this way first. It'd be f of 1.1, and that would get multiplied by the delta x, the width of the interval, so multiplied by 0.2. And then plus my second rectangle would have a height of f of 1.3 multiplied by a width of 0.2. My third rectangle would have a height of f of 1.5 multiplied by a width of 0.2. Fourth interval, f of 1.7 times a width of 0.2. And the last one, a height of f of 1.9 times a width of 0.2. Okay, so then what I'm going to do here, all of them have the same width of 0.2. I could have done this right away, so I'm going to factor that out and just say 0.2 times the sum of all of the heights. So f of 1.1, you'd be plugging 1.1 into 1 over x. So that height would be 1 over 1.1. Plus f of 1.3 would be 1 over 1.3. Plus f of 1.5 is 1 over 1.5. Plus 1 over 1.7 plus 1 over 1.9. So this is what you'd be calculating to approximate that integral using the midpoint rule, or using 5 rectangles with midpoints. Then how the formula looks? Yes, I know. I provide it so you see the notation, but yes, just understanding what you're supposed to do.
Oh, good. So is it 0.6932?
Yes. All right, yes, when you calculate this, and again, always round to at least 3 decimal places. You can always round or have more decimal places, have at least 3. It's approximately equal to 0.692. Why is it an underestimate? How do you know it's an underestimate? Oh. In order to really understand whether or not midpoint is going to give you an under or an overestimate, we talk about that more once once I show you how to use a trapezoidal sum to estimate.
Did you know it's Capri season?
Okay, Dylan, yeah, question.
No, it's different. Wait a second. It's different.
Okay.
Season, bro.
Okay. All right, so I'm going to pass out then. I also want to cover properties of definite integrals with you, which is on a separate sheet.
We weren't raised in the barn. We were raised on the lake.
There's so many people out there. Oh, I saw that. I'll try that. You can't get out there now.
All right. So this second part, the properties. Properties help us evaluate integrals. So once we get into 5.3 and we're evaluating not just by approximating or by using areas, we can actually evaluate them. These properties can help you in terms of breaking apart integrals to make them easier to evaluate. So looking at these properties on here, and I'm going to explain or help you make sense of why the rules are what they are. So it doesn't seem like something you just have to memorize. When the definite integral from a to b of f of x dx was defined, we were implicitly assuming that a was less than b. So if you have an interval from a to b, a is assumed to be the smaller number, b is assumed to be the larger number. So the definition as a limit of Riemann sums makes sense even if your a value is greater than your b value, if they're flipped around. So if we reverse a and b, then this was the original formula for calculating delta x. If a and b are now switched, that means it is really the opposite of what it was before. So a minus b is the opposite of b minus a. It would be as if you're factoring a -1 out of the top. So because of that negative there that's now in delta x, if you have the integral from b to a instead of from a to b, it equals the opposite of the integral from a to b. Okay, so if you switch the limits of integration for an integral, if they're switched, you're taking the opposite of that integral then. The integral value would become the opposite. So say you had the integral from, it was given to the integral from 3 to 2, and you switched it so now it's 2 to 3, you would have to make sure that you're taking the opposite of that integral then, the opposite value. So that's one property. You switch the limits, it's now the opposite value. We also then have, so that's if a is less than b, a is greater than b. If a is equal to b, then when you calculate delta x, so if a and b are the same, rather than having a minus b here, you would have just a minus a or b minus b. Either way, it's 0. And therefore, if there's no change in x, the integral itself is just 0, because your width would be 0. So any area of a rectangle with a width of 0 is going to be 0. So if you have an integral where the limits of integration are the same, it's equal to 0. So the integral from 2 to 2 of any function would be 0. And then I numbered the properties below the same way they're numbered in the book. So if you're working through any problems and it mentions property 3, you can even look on your sheet and know what property they're talking about. But these are just basic properties. We're assuming with these properties f and g are both continuous functions. And these properties are true whether or not a is less than b, equal to b, or greater than b. So if you have the integral from a to b of a constant c, then it is equal to c times b minus a. So the reason why I included this diagram for you to understand why this rule is true. Here the c is your function. This is like f of x equals a constant. So you have a constant function. A constant function is a horizontal line. And then if you have limits from a to b, what you're creating is a rectangle with a height of C and a width of B minus A. And the area of a rectangle is length times width or base times height. That's where the C times B minus A is coming from. So the integral of any constant from A to B, the value of that integral is C times B minus A. And then, I know the 2 got cut off here. 2 and 4 are very similar. So if you have the integral of a sum of 2 functions, it is equal to the sum of 2 integrals. So you can say the integral from a to b of f of x plus g of x is equal to the integral of f of x plus the integral of g of x. And then same for differences. You can split an integral of a difference of 2 functions as the difference of 2 integrals. When you have the integral of a constant times a function, you can bring that constant out front and just find the integral of the function and multiply that by the constant. So some of these are very similar to those limit laws or limit properties we worked with. And then the last one, the 5th one, is you have to look at your limits of integration. And it goes with this diagram over here. So notice on this diagram we have y equals f of x, and then we have the interval from a to b, but there's a c value somewhere in between a and b. So we can then say the integral from a to c plus the integral from c to b should equal the integral from a to b. So it's saying the area from a to c plus the area from c to b should equal the total area. And that should intuitively make sense. We'll go through problems where you actually use that type of property. So here's 2 examples using some of the properties from above. So it says use properties of integrals to evaluate the integral from 0 to 1 of 4 plus 3x squared dx. So I'm going to show you how to rewrite this so that we can apply these properties. First of all, I have a sum of 2 terms, 2 functions I could think of them as, so I can split this into 2 integrals. I can say that this is equal to the integral from 0 to 1 of just 4. Make sure you include, though, the dx after each integral, and then plus the integral from 0 to 1 of 3x squared dx. So that's using the second property. You don't have to write that down. That's using the second property. Then, before I do anything with this integral, I'm just going to leave it for right now. But for the second one, that coefficient of 3, I can actually write in front of the integral and say this is 3 times the integral from 0 to 1 of x squared dx. And then, to evaluate that first integral, 4 is just a constant, so it would be using that first property. So I can say this is equal to the constant of 4 times the width of the interval, which would be 1 minus 0. So that's using that first property. Okay, so that integral just has a value of 4. 4 times 1, 4. Then, this would be 3 times, now, this integral, the integral of x squared, I included this because this happens in some of the practice I included as well. We actually found the value of this integral in section 5.1. So right now, you're not just expected to know if I give you the integral from 0 to 1 of x squared what the value is, but they're using this because this is not from one of the properties above. This is from 5.1. We found this value to be 1/3. So this was from 5.1. So if you are expected to know anything like this in a problem, they will tell you if the integral from 0 to 1 of x squared dx equals 1/3, find, and then it would give you a different integral, and you would have to know then to substitute that in where appropriate. So you're not just expected to know that. So then from here I would just evaluate this. So this is just 4 plus 3 times 1/3 is 1. So the value of this integral is 5.
Why do you like in the properties? Is that just kind of something that they teach just to teach, kind of? Because like you wouldn't really need it, like you could solve without it.
Yes, but this is just saying, like, you could still split it apart and now just find the antiderivative of each. I mean, that's what you're doing anyway. But right, the thing is, not everybody knows that yet. And even using that, I still use these properties a lot when I work through different problems.
You like my beard?
Just to make it easier to work through.
Like my beard?
You will see problems probably using the fifth property quite a bit.
It's true though. You like my beard?
It's great. All right, example 2. Using the properties above, what would the integral from 1 to 1 of x squared cosine of x dx be? 0.
Oh, what's up?
Done. The interval 1 to 1 means there's no area.
It would just be a point, or no, it'd be a line.
Yeah.
Line segment.
All right, and then example 3.
You have to memorize the properties.
Oh, that's like kind of bad.
That's why I went through and explained them, so you don't have to see it as just memorizing. If you understand what they are, you don't have to memorize them. What?
Sorry.
All right, quiet please. Thanks. The third example is also using those properties. So you have the integral from 0 to 10 of f of x dx is 17. The integral from 0 to 8 of f of x dx is 12. And it wants you to find the integral from 8 to 10 of f of x dx. So here, look at the intervals that you have and try to, or it can be helpful to set up an equation with the intervals that you have. So it looks like we have 0 to 10, 0 to 8, and then 8 to 10. So we're starting at 0, going to 10, and somewhere in there we have 8. Okay, so this would mean, not that you would have to write this out, I just want you to understand it. This means that if I have the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx, that would equal the integral from 0 to 10 of f of x dx. So 0 to 8 plus 8 to 10 should equal 0 to 10. Then, yes, then you can insert the values you already know. We are trying to find 8 to 10. We know 0 to 8 is 12, and 0 to 10 is 17. So yes, 12 plus what is 17? This means the integral from 8 to 10 of f of x dx is 5.
Dang. I kicked that one, bud.
Any other questions? Yes. Not very well, but yeah.
Why did you guess?
Why is there? It's part of the notation. It doesn't mean anything on its own right now. Yeah. Yes. So it should be there. It's part of the notation for an integral. Okay, then the last example, we have some comparison properties for integrals.
Oh no.
And these are only true if A is less than or equal to B. So, I need it quiet, please. The first two, 6 and 7, again, I numbered them how they're numbered in the book. 6 and 7 are pretty intuitive. Can I please have it quiet so I'm not talking over people? Thank you. So if f of x is a function that's greater than or equal to 0 on the interval from a to b, then the integral from a to b of f of x dx should also be greater than or equal to 0. So if you think about that, if a curve is above the x-axis on the entire interval a to b, then the area under the curve should be positive, because the area under the curve between the curve and the x-axis would all be positive area. And then 7, if f is greater than or equal to g for the interval a to b, then the integral from a to b of f should be greater than or equal to the integral from a to b of g. So if f is a greater function than g, so on a graph f would be higher than g is, the area under f should be larger than the area under g. That's intuitive as well if you kind of pictured it. A higher or a greater function would have more area below it. The last one, though, I'm going to talk about, and then we're actually going to use an example for. So this says if f of x is between two values, little m and capital M, for a to b, then the integral from a to b of f of x is between these two values, little m times b minus a, large M times b minus a. So m, these are just representing numbers. So what this would mean on the closed interval from a to b, little m would represent the absolute minimum of f of x on that interval. Capital M would represent the absolute maximum. All right, so here's kind of the why this ends up being true. I'm going to start with this. So if you know on a closed interval what the absolute min and max of a function are, and you were trying to estimate the integral of f, what they're doing to get from this statement to the conclusion is they're then taking the integral of everything. So they're taking the integral from a to b of little m dx, the integral from a to b of f of x dx, and then the integral from a to b of capital M dx. And then as I said, little m and capital M are the absolute max and min. So they are constants. So by the first property we saw on the front, this integral would be equal to the constant multiplied by the width of the interval b minus a, which is the right or the left side of our conclusion. We still have our integral of f in the middle, and then the integral on the right side, the integral of capital M would be capital M times b minus a by that first property. So these are both going to be values here. This is just giving you an estimation and saying the value of the integral is between these two values. So it does say below when you would use this property. Useful when all we want is a rough estimate of the size of an integral without going to the bother of using the midpoint rule or finding a more specific estimate. So they might just want a rough estimate of two values that's in between. This is one way to get that estimate. So I just want to show you how to use that property. And some problems, again, in the practice will say use property 8, so it is numbered how it is in the book, to estimate the value of this integral. So what I'm going to do, this means our function f of x is e to the negative x squared, and we're on the interval from 0 to 1. So I'm just going to graph that function from 0 to 1. Oops, I didn't change my window. Yes. All right, so my y scale is not the greatest. I could change it. So what's happening, and if you wanted to find these exact values, what I can see is for the entire interval, though, it is decreasing. So when x is 0, that is actually giving us the absolute maximum. And then when x is 1, that is giving us the absolute minimum on that interval. So I could use my calculator to find the absolute maximum, or I could just plug in the endpoints into here. So I said the absolute minimum is when x is 1. And if I substitute 1 in for x, I would have e to the negative first. So I know right now that e to the negative x squared, the absolute minimum is e to the negative first. And then the absolute maximum was when x was 0, and that would be e to the 0, which is 1. Okay, so I have an absolute max, and min. And so then to get the rough estimate, I can take the integral from a to b, or which would be from 0 to 1 of everything. And that means the two outer integrals, since they're constants, they're just going to be equal to that constant multiplied by the width of the interval. So I would have e to the negative first multiplied by 1 minus 0 is less than or equal to the integral from 0 to 1 of e to the negative x squared is less than or equal to 1 times the width of the interval, 1 minus 0. And those integrals, because of our width of our interval just being 1, is actually just equal to the absolute maximum anyway. So I would have e to the negative first is less than or equal to the integral is less than or equal to 1. Or you could have for e to the negative first, you could approximate that, so this would be about 0.368. No, I did not. Okay, so it wouldn't always come out that way, that the absolute max and min actually are the upper and lower bounds of the integral, unless the width is 1. But that's how that property would be used to give you a rough estimate. Oh, this one? Yeah. Sorry, I missed that. Okay, so what I have included on here, I just want to point this out. 1 up to 33, that was on the previous assignment as well. And some of those I had marked that you could have done already, but these were from the previous assignment. These are really the new ones for this specific sheet. Just pointing that out. So it's not between the. This is between the two lessons, not just this one.